All right, so we're going to be jumping back a few chapters now to chapter 13 to look at solutions and different properties of solutions, including different ways we can represent concentration, as well as different factors that are going to influence the solubility. And when we're looking at a solution, we want to recognize it's going to be a homogeneous mixture, meaning that we're going to have an even distribution of the different materials in there throughout the entire solution. And what we're looking at, we've got two different pieces. So the solvent is going to be typically the thing that we have the most of. And you can kind of think of that as the thing that's doing the dissolving. And then the solute is the substance that we're dissolving, essentially. So if we think about a salt water solution, we're thinking about the solute as the salt, and then the solvent is going to be the water itself. And for the most part, water is going to be the most common solvent, but it doesn't necessarily have to be the solvent. So in the case of air, that's actually going to be a solution itself. With it, it's a little bit sometimes misleading depending on how we're thinking of it, because there are going to be different concentrations of things at different points in the atmosphere. But if we're thinking about just air within a room in sort of a small area, it's going to be, for the most part, pretty evenly mixed. So we could consider that to be a solution. But with the rest of these, we're kind of thinking of the same thing. We're still just going to have that mixture that's going to be even throughout. So if we took two different samples of it, we would wind up with the same percentages of the different components. And that's why if we just think about a saltwater solution again, if you took like a sip of a cup of water that you added salt to, you would taste salt in each of those sips. You're not going to get one that's extremely salty and then one that's not salty at all, because it is going to be homogeneous, meaning it's going to be even throughout. And when we're looking at solutions, the reason things are going to dissolve is because the intermolecular force, or the intermolecular attraction between the solute and the solvent is going to be greater than just the intermolecular force between the solvent individually or the solute individually as well. So when we look at an ionic compound, for instance, we can think about the water in red and white, and then whatever the ionic substance is going to be in purple and green, and we're just going to see the overall energy in terms of Gibbs free energy, we'll ultimately see is just going to decrease. So click through there. And if we think about an ionic compound and actually sort of follow it through the entire piece, we can kind of think of it as, if we think about it as sodium chloride, so green being the chloride, purple being the sodium. We could take it and throw in a handful of the solid, but because it's going to be soluble, we're going to see that the ionic compound is essentially going to get ripped apart into the individual ions. Then the water molecules are just going to surround them, so that the positive hydrogen are going to be sort of pointed at the negative chloride, and then just the reverse, the negative oxygen of water is going to be pointed at the positive sodium. But the interaction between the water and the solvent is going to be a more stabilizing interaction than just having the solvent and the solute essentially separate from one another. And with this, we can think of it as an ion dipole, because we got the dipole, or just the dipole, excuse me, of water. Oxygen going to be negative, hydrogen going to be positive. And then we've got the ion piece, just with the anion, in this case chloride, the cation for sodium. So we're just going to see the interaction between those two. And that interaction is just going to be enough to overcome the lattice energy. So that's thinking about the ionic force holding together those two ions. And then with this whole process, we can kind of think of the solute and the solvent separately. So initially, we're going to have just kind of the pure for either one. But then when we have the dissolution process occur, so when we actually take that substance and dissolve it in the solvent, we're going to see that the solute's going to spread out. We're going to see some spreading out of the solvent as well. And we can kind of think about the combination of those as the change in energy throughout the entire process. And then this is kind of just showing you the same thing here. It's just now we're actually kind of putting it into more of a quantitative sort of steps. So we're starting with, if you think about it, just see the pure solvent and the solute. And we're going to see there's going to be an increase in energy to separate the solute particles. Same thing, increase in enthalpy, I should say, to separate out the solvent particles. But then when we take all of those together and mix them into the solution, we're going to see a large decrease there. So overall, we're going to see for the most part, the process of dissolution, so just dissolving something, we're going to see for the most part is going to be considered an exothermic process. So we're going to see a negative delta H. We're going to see something that's going to release energy. It's going to release heat. So we're going to feel this reaction if we actually take something. So sodium hydroxide is a pretty good example. If you take that and actually dissolve it in water to make the sodium hydroxide solution, it's going to feel warm while you're doing it, because it's going to be an exothermic process, because the process of actually forming the solution is going to release that heat, going to release that energy. But that's not always going to be the case. So if you've ever used one of the ice packs that you kind of have to crush in order to sort of activate and sort of to get the cold sensation, that's going to be actually from dissolving something. It's going to be from dissolving ammonium nitrate, excuse me, not sodium. So ammonium nitrate, NH4NO3. And when we actually take the packet and crush it, it essentially allows the little capsules of water and ammonium nitrate to mix, allows that solution to be formed. And then overall, if we look in this case, we're seeing a net increase in the delta H. So we're seeing an endothermic process that's absorbing energy. And that's why it's going to feel cold, because it's actually taking energy from the surroundings, and we're considered part of the surroundings there. So with this dissolution, typically, we're going to see it's going to be an exothermic process, but that's not always going to be the case. And the reason for that, as we saw in the thermochemistry chapter, is going to be because there's more than just enthalpy to consider. So there's also going to be that entropy component, and ultimately we're going to be focused on the Gibbs free energy change if we're trying to determine what a spontaneous, or if a process will be spontaneous or not. Because in addition to the enthalpy change, we've also got entropy. So you can kind of think about it here. If we're mixing 500 milliliters of carbon tetrachloride with 500 milliliters of hexane to make 1,000 milliliters, or just 1 liter of the mixture here of this solution, we're going to be going from low entropy to higher entropy. So we're going to have even or split halves, I guess, into just the full mixture. So we're going to see an increase in entropy throughout this process. And that's why we need to consider Gibbs free energy rather than just enthalpy when we're looking to try to determine if a reaction is going to be spontaneous or not, because we may see the enthalpy change may actually be positive, so it may be endothermic. But if we've got a large increase in the entropy, then we can overcome that enthalpy aspect. And with this, just to point out, there is going to be the case where things look like they're dissolving when they may actually just be reacting instead. So there is going to be a difference between dissolution, or that process of dissolving something, and a chemical reaction. Because with a solution, we're going to be able to obtain the solvent just by evaporating off we're going to be able to obtain the solute, excuse me, by evaporating off the solvent, where in the case of the reaction, that's not going to be possible. So if we look at the ones here, this is showing hydrochloric acid with some sort of metal. And what we're going to see in that case is that's going to produce hydrogen gas. We're actually going to have a single replacement reaction occur. So we're not actually going to be dissolving that substance. Whereas if we take something like this, dissolve, but we get that green solution. If we then evaporate it off the solvent, we would just be left with that substance again. But in this case, if we react the metal with the acid and then evaporate all of the liquid, we're not going to be able to obtain that solid anymore, because we had a reaction take place. We converted it into a different substance there. So with the dissolution process, it's just a physical change. And that's why in Gen Chem 1, you should have done a separations of a mixture lab where you can actually take salt and sand, dissolve dissolve the salt, excuse me, filter out the sand, and then just evaporate off all the water to recollect that salt, because it's just a physical change. We're not actually changing it via a chemical reaction like we would with metal and acid. And then when we're looking at solutions, there's going to be different sort of terms or ways we can categorize them in terms of how much of a substance is going to be dissolved. So we'll see later on in the chapter, there's going to be different ways that we can actually quantitate it in terms of what units we want to use for like concentration. But in this case, we're just kind of looking at it in more of a qualitative respect in terms of just how much stuff have we dissolved compared to how much can we dissolve. And when we're looking at a saturated solution, and it's going to be a different amount depending on the solvent we have, depending on what solute we're using. So we can't just take any two substances and then always dissolve the same amount. There's going to be different factors we'll see as we go through this. But a saturated solution is just going to mean that at that specific temperature, we've dissolved as much of the solute as we possibly can in that amount of solvent. So if we're thinking about sort of percentage-wise, how much it is dissolved, a saturated solution is going to be 100%. So if we added any more of that solute to the solution, we've already reached the saturation point. We're not going to be able to dissolve anymore. So we just kind of see that float to the bottom and settle out there. And then if we're below that sort of maximum, that threshold, we're going to consider that to be an unsaturated solution, just because we're still going to have the ability to dissolve more of that solute. And then with the dissolution process, you can kind of see, like we mentioned earlier, the water molecules kind of just surround the solute itself. So if you want to, you could think of a saturated solution as we're using up basically all of the water molecules we have there in terms of dissolving that substance. Whereas an unsaturated solution, we're still going to have free water molecules to continue to dissolve more of that stuff. And then there's going to be sort of a unique kind of weird case where we're actually above that threshold. And in that case, we're going to refer to it as a supersaturated. So if you think about like a superscript, is going to be something that we write in sort of the position of an exponent, because it's going to be above the normal text. So a supersaturated solution is just going to be a solution that contains more of that substance than could normally be dissolved under those conditions, meaning the temperature and the amount of solvent. And then this is going to be something that you may be familiar with if you've ever made like rock candy or anything like that. You take a pot of water, heat it up, get it boiling, add a whole bunch of sugar to it, because it's going to have higher solubility at that higher temperature, so we'll be able to dissolve more of it. But then we cool it down, and then as we cool it down, the solubility decreases. But because that substance is already dissolved, it can actually stay dissolved. And it'll stay like that until we do something to disturb it. And in some cases, like they're showing here, it's kind of hard to see, but if you look, they got tweezers, and then there's just one little crystal at the end there. So that would be the example of a seed crystal. And it's called that just because it's going to essentially serve as a seed for the crystallization process to occur. So you can see when it's added, we start to get the solid forming around it. Until we ultimately just get a whole bunch of that solution crashing out, or that's the solute crashing out of solution, I should say. But with it, in some cases, even just sort of shaking the beaker, the container, is enough to disturb it and have that recrystallization process occur. Or even if just like a speck of dust floated in there and landed on the solution, that could also cause the crystallization to occur, because at these conditions initially with this supersaturated state, we've dissolved more than, or we have dissolved more than could normally be dissolved in that solvent. So it's just going to be sort of an unstable condition. So once we do something to disturb it, throws off the stability, and then we have that solute crash out of solution. So we reform the solid there. And then again, with this one, just note that in order to make a supersaturated solution, you've got to heat up the solvent and dissolve enough of it at that higher temperature, and then cool it down. You can't just go to whatever temperature you want and then just add a whole bunch in there, because otherwise you'll hit the solubility sort of threshold where you've dissolved 100 or as much as you possibly can. So when you start to add more of it, at that temperature, it's just going to float to the bottom. We're not going to be able to dissolve any more of it. But at the higher temperature, where we've got increased solubility, we can dissolve extra of it and then cool it down, and it stays dissolved until we do something to disturb it like we did here. But in terms of solubility, like I mentioned, the solute, the solvent, the temperature are all going to be important. So what we're trying to dissolve, what we're trying to dissolve it into, and at what temperature are we having that occur, are all going to be critical factors in terms of the solubility, which is just going to be a measure of how much of that substance can we dissolve in the solvent. So when we're looking at solubility, we've always got to specify what it is that we're dissolving in, because you can see here the solubility is going to be different when we're dissolving it in water versus dissolving it in hexane. And then the big thing with solubility is this term, or this phrase, like dissolves like, meaning that a polar substance usually dissolves well in other polar substances. And then the same thing with nonpolar substances in a nonpolar solvent. So when we look at these examples here, just keeping that in mind, we can kind of, based on what we know about water being a highly polar molecule, and then having essentially infinite solubility for these first three, with much lower numbers for the next ones, we can kind of assume that we're going to have much more polar molecules with these first few alcohols than we will for the rest of them. And that kind of makes sense just looking at the molecules themselves, because in each case they're considered an alcohol just because we've got that OH group at the end. But then we've got a increasing size to the carbon chain. So we kind of have the rest of this molecule that's going to be considered nonpolar. So with methanol or ethanol even, that nonpolar section is pretty small. So the hydroxy group, this alcohol group, is going to have a relatively large impact. That's why we see it's going to be pretty polar here. That's why we've got the infinite symbol. Whereas when we get to these larger alcohols, now the nonpolar piece makes up a larger percentage of that molecule. So it has a larger impact. That's why we see the solubility decrease. So as we're going down this table, we'll see the polarity decrease of these different alcohols. So that's why in water, we see the solubility decrease as well. Whereas in the hexane, which is going to be a nonpolar solvent, it's just going to be a string of carbons with hydrogens attached to them. It's going to be completely nonpolar. So we're going to see as we go down this list, the solubility increases. And that's why initially with methanol, which is going to be the most polar of these, we can only dissolve 0.12 moles of that substance in 100 grams of hexane. Whereas we move down, we get less and less polar. So we see in this case, they're all just represented with the infinite symbol. But we're seeing the solubility increase in general as we go down that, just because these are going to be more nonpolar, so they'll dissolve better in that nonpolar solvent. So like dissolves like just means polar dissolves in polar, nonpolar dissolves in nonpolar. And the reason for that, if we think back to what we mentioned earlier about the intermolecular attraction between the solvent and the solute, sort of overcoming the intermolecular attractions of just those pure substances, so the pure solvent, pure solute, we're going to see the reason like dissolves like is because when we've got more similar intermolecular attractions between the solute and the solvent, it's just going to increase that solubility, just because it's going to increase the attraction there. So with this one, we're looking at two carbons. So we're looking at ethanol. And we can see if we had two ethanol molecules, we're going to have hydrogen bonding there because we've got the OH group. So oxygen's bonded directly to hydrogen. So we've got a negative oxygen attracted to the positive hydrogen of another. And the reason then that we're going to see ethanol is going to dissolve well in water is because we can have that exact same interaction occur. And then again, with ethanol, we've only got two carbons there, so this hydroxy group's a relatively large portion of the molecule. So that's why we see this solubility is going to be relatively high. But then if we added a whole bunch of carbons here, like we saw with the table on the previous slide, as we moved down there, we just had more and more carbons. So then we would have a larger nonpolar piece, which would kind of just minimize this interaction. So that's why we see the solubility decrease as those alcohols got larger and larger. And related to that, if we look at these two molecules here, look very similar. So in this case, it's just going to be an orientation or a representation of two different carbons, carbon-based molecules, I should say. So glucose on the right, and then this is going to be cyclohexane. So you've just got, in this case, each of these corners, basically, where the lines meet, represent a carbon. And then coming off of those, we've just got hydrogens to fill in the rest of the bonds. Whereas with the glucose molecule, we don't just have hydrogens. You can see in one spot we've got oxygen, but now we've got a whole bunch of these hydroxy groups. We've got these OHs representing the alcohol groups. So what we're going to see in this molecule is now we've got the ability to hydrogen bond, which we don't have here, because even though we've got a whole bunch of hydrogen, it's bonded just to carbon. Remember, with hydrogen bonding, we need fluorine, oxygen, or nitrogen. So that's why we're going to see in this case, glucose is going to have a much higher solubility in water than the cyclohexane would. But now if we took these same molecules and tried to dissolve them in hexane, so just regular hexane, it's just going to be 6 carbons in a row. That's going to be a nonpolar molecule. So we'll see the cyclohexane, also nonpolar, going to have a much higher solubility there. Whereas the glucose, not going to be able to dissolve nearly as well if we can get it to dissolve at all. All right, so now if we look at two different vitamins here, vitamin A, you can see got a whole bunch of carbons, some hydrogens lifted in there, and then just with the one hydroxy group on the end, so the one OH. So we're going to consider this to be relatively nonpolar, whereas vitamin C going to be the opposite. We've got a whole bunch of these hydroxy groups, way less carbon, so this is going to be a much more polar molecule. And that's why we're going to see the vitamin C is going to be much more water soluble, so it's going to be a lot better at dissolving in water. Whereas vitamin A going to be the opposite, and that's why with compounds, especially if you're looking at environmental contaminants, there's what's known as biomagnification, bioaccumulation, where these substances can actually build up and increase in concentration in different organisms, either individually or as they move through the trophic levels, to just basically up the food chain. And with those substances that can bioaccumulate or biomagnify, those are going to be fat-soluble substances. So they're going to be nonpolar, sometimes referred to as hydrophobic, because they don't mix well with water, or lipophilic, because they're much better at absorbing in fat. But these type of nonpolar substances are going to be much more readily bioaccumulated or biomagnified, just because they're going to be able to essentially sort of dissolve into your fat and just get absorbed and stored in fat. Whereas something like vitamin C, that's going to be considered water soluble, it's just going to be excreted from the body much quicker, whether it's just through urine or even in some cases like sweat or respiration. But it's just going to be excreted much quicker, because it's not going to wind up getting stored in fat like the nonpolar substances will. And then when we're looking at gases in particular, there's going to be certain things that are going to impact those, including the molecular mass, because that's going to imply greater dispersion forces. But the main thing that we're going to be looking at with the solubility of gases is just going to be kind of shown here, and it's going to be the pressure itself. Temperature as well, that'll affect liquids and solids as well. But with the gases, if you think about just opening a can of soda or something, originally it's going to be under high pressure, so we're going to have a relatively large amount of the carbon dioxide actually dissolve there. But then once we open the can, we release some of that pressure. What we're going to see is the solubility in that case is going to decrease, and that's why when you open the can of soda the first time, you can kind of hear that gas being released just from the decrease in that pressure. So we're not going to have as much of it dissolved anymore. And that's why if you look at it in this case, it's kind of going in the opposite direction. We're taking the piston and pushing it down. So we're increasing the pressure here. And that's why we can see more of the substance is actually dissolving. And then to quantitate that, there's just what's known as Henry's law. So S is just going to be representing the solubility of that gas. K is going to be the Henry law constant. So it's going to be dependent on what we're considering the solute to be. So whatever gas we're focused on, as well as the solvent, excuse me, that we're dissolving in. And then the pressure here is just going to be the vapor pressure we have of that gas above the liquid. So if we think about just a can or a bottle of soda in this case, we're originally going to have a whole bunch of that carbon dioxide dissolved. We'll have some of it in the gas phase here. But then when we open the bottle, we release that pressure. So we're releasing some of that gas. The vapor pressure decreases. So if we think about the calculation here, if we're decreasing the term on the right, we're going to wind up decreasing the term on the left as well. So that's why when you open the bottle or the can of soda, you hear that gas being released. We decrease the solubility of the soda. And that's why you can hear the sound. With this, I'll come back to this in a second because I just want to talk about a couple of slides here with the factors as well. But with it, like I said earlier, solubility typically increases with temperature, and that's going to be when we're looking at solutes that are going to be solid, so something like potassium nitrate, these ionic substances, you can see all have kind of an upward trend for the most part. Sodium chloride kind of flat there. Cesium sulfate, excuse me. We do have a decrease with, but for the most part, you can see that we're increasing the solubility of these substances as we increase the temperature. And then with this graph, also just note that on the y-axis, the solubility is grams of salt, so grams of whatever substance we're focused on in 100 grams of water. We've got to specify how much of that solvent we have, because if we had 1,000 grams of water instead of 100, now we've got 10 times as much of the water. The solubility itself hasn't changed, but the amount of that substance that we can dissolve is going to be 10 times greater, because now we just have 10 times as much of the solvent. So when we're looking at a solubility thing like this, we've got to always specify how much of the solute in how much of the solvent. But with gases, what we see is just the opposite. So as we increase the temperature here, we're seeing a decrease in solubility. So in this case, we're showing it in concentration of millimolar. But you can see with all of these different gases, and you can see they follow the trend of increasing molar mass for the most part. You can see methane's a little bit of an outlier there. But we can see that with all of them, as we increase the temperature of that solvent, we see a decrease in the solubility. And that's why soda, if you leave it out just on the table or something, it's going to warm up. So it's going to go flat faster. You're going to lose the carbonation quicker. And then this is going to be important environmentally for multiple reasons, because if we think about the planet as a whole currently, we're increasing the temperature just through global warming. So increase consumption of fossil fuels increases the amount of greenhouse gases, so we can keep the heat from solar radiation into the atmosphere more, which ultimately heats the oceans, heats the rivers and things like that. So if we think about what's living in those in those waterways, they're going to need oxygen. If we think about the fish and things, they're going to need oxygen. But if we're increasing the temperature, we can see the solubility of that oxygen is going to decrease. So there's going to be less oxygen available. It's just going to be a less friendly environment to them. But then with global warming as well, if we think about CO2, we don't have it here, but it's going to follow a similar trend, whereas the temperature increases, that solubility decreases. So with the fossil fuels, we burn them, we produce carbon dioxide, stays in the atmosphere, but some of it actually dissolves into the oceans and things like that. But as we start to heat up those oceans, now we're going to decrease the solubility. So what we're going to see is some of that carbon dioxide then is essentially going to undissolve. You can even think about methane as the same thing, because methane is an even worse greenhouse gas. It's just less abundant in the atmosphere, but it's going to have a more impactful effect if we're thinking about just one molecule of methane versus one molecule of carbon dioxide. It's got a larger global warming potential. But we can kind of think about it the same way, as we're going to have some amount of it dissolved in the ocean. So let's say if the ocean's 10 degrees, we can dissolve this much. But now as we start to heat it up more and more, we're going to decrease that solubility. So we're going to have some of that greenhouse gas re-enter the atmosphere. It's then going to further increase global warming. So this is just going to be one of the many reasons environmental issues can just be so complex. They're going to be so multifaceted, just from the science perspective, without also even considering the economic or other implications that need to be considered with those types of decisions. But to go back to this question here, we're thinking about Henry's law and the solubility of those gases. So again, carbon dioxide is going to be the carbonation in soda. So if we look at this question here, the partial pressure of carbon dioxide inside a bottle of cola is 4 atmospheres at 25 degrees C. What is the solubility of carbon dioxide? And then the Henry's law constant for CO2 dissolved in water is 3.3 times 10 to the negative second mole per liter atmosphere at 25 degrees C. So if you want to take a moment to work through this yourself, just pause the video, because I'm going to start going through it in a second. I just got to grab something quick. Oops. All right. So with this one, we want to remember solubility. Henry's constant, although I think actually on the previous slide, I think the textbook uses K as the Henry's law constant. Yeah, so they use K instead of H. But it's going to be the same thing, where we're essentially just going to have to take the Henry's law constant. So in this case, 0.033. And if we think about moles per liter atmosphere, that would be molarity over atmospheres. Times the vapor pressure. So in this case, just 4. And that's ATM. So with this, we're going to see that the pressure units are going to cancel. And then we'll get 0.132, I believe. Yeah. But with sig figs, we've only got 2 of them. So we'll just round it to 0.13. And then with this, the solubility in this case is going to be moles per liter. So we can dissolve at 25 degrees C at with a vapor pressure of 4 atmospheres, because if we open that bottle, the vapor pressure is going to decrease as that gas escapes. So the solubility is going to drop a lot. But under these conditions, we can dissolve 0.13 moles of CO2 for every liter of water we have. And then with it, it doesn't specify units in this question, so we can just keep it exactly as it is. If it wanted it in terms of grams per liter for the solubility, then we would just have to use the molar mass to convert moles to grams. Or if it wanted the volume in something else, we can do the same thing, where we just use a conversion factor. So we just have to make sure that we're paying attention to units, so that whatever unit we're focused on. So if we wanted to go moles per gram, moles to gram, I should say, then we would just have, for carbon dioxide, 44.01 based on 1 carbon and 2 oxygens over 1 mole. So we just want to make sure that the moles are opposites there, so they cancel, and then we're just left with grams per liter. But with this, that'll be the end of this first video for the solutions chapter.